Start. Start.
Okay, let us start. So we have seen what is a simplex in an Euclidean space Rn, right? So so we have seen to recall if we have V naught, V1 and so on, V K, right? Uh, points, right? In Rn, right? And if they are affinely linearly independent, or you can say that they are in a general position, that is this set is linearly independent, then this set uh, TIVI this is this set this is in Rn is called a simplex spanned by these uh, points, and these points will be called vertices of the simplex. This one. Uh, now and also we have seen that a zero-dimensional simplex, it is just point, right, in Rn. One-dimensional simplex, it is just, you can see, closed interval. Two-dimensional simplex, it is triangular disk, right? Three-dimensional disk, simplex, it is tetrahedron, right? So and so on. Now a Euclidean simplicial complex is a collection K of simplicious in some Euclidean space Rn, satisfying the following conditions. Satisfying the following So first condition is that if sigma belongs to K, right? So what is K? K is a collection of simplices in some Euclidean space, right? So this first condition is if sigma is a member of K, then every face, then every face of sigma is in, right? So for example, if sigma is a this two-dimensional simplex, right? So if this is there in K, then this definitely this space will be there, this space will be there, and this space will be there. So these are one-dimensional faces, and then zero-dimensional face. This one, this vertex, this one, they also will be there. Second condition is the intersection the intersection of any two simplices to simplices in K is either empty or a face. So if you take any two simplices in K, then either they don't intersect, or if they intersect, then their intersection is a common fit, right? So if you take a simplex, suppose something like this, and another simplex, suppose this two-dimensional simplex, then this is one-dimensional simplex, this is two-dimensional simplex. So their intersection will be just this face, zero-dimensional face of this and zero-dimensional face of this. Okay, it is not possible that it is not. I mean, it is not possible to have condition something like this, right? So it is not possible to have something like this. Right? This is a simplex. Right? This kind of intersection is not allowed. Okay. Also, it is not allowed. Yeah. Yes. This is this. Then we have third condition. K is locally finite collection. That is, every point of Rn has a neighborhood intersecting at most finitely many simplices of K. right? So what does it mean? That means that if you have a situation something like this is not allowed, right? That you have, uh, means, for example, infinitely many simplices cannot have a common uh, face, can say. So for example, this is not allowed. It's not allowed to have something like this. That infinitely many two simplices intersecting at one point, having a common vertex. This kind of situation is not allowed. Okay. Similarly, infinitely many uh, two simplices having a common one-dimensional face. That is all. That also is not allowed. Uh, but we will be interested actually in uh, uh, finite simplicial complexes, right? So the third condition will be redundant because finite simplicial complexes means simplicial complexes having only finitely many simplices. Uh, so we have a remark. The local finiteness condition implies that k is countable because every point because that local finiteness means every point of Rn has a neighborhood, and hence you can say an open neighborhood has a neighborhood intersecting at most finitely many simplices of k, right? So each point of Rn, because of local finiteness, each point of Rn will have a open neighborhood intersecting only finitely many simplices of k, right? So we can say that there is an open covering of Rn such that each member of the cover intersects at most finitely many members of k. Okay. Now, because Rn is countably compact, right? So every open covering has countable subcover, right? Uh, so what we have is there is a so yeah yes, so we can choose a countable subcover of Rn, and because each member of that cover intersects only finitely many members of k, so k is going to have count because you see we have some, this is a countable cover of Rn, and each ui intersection k, this is finite. Suppose this is vi, this finite, right? Then what will you have? Uh, k will be actually vi uh, I belonging. But these VIs are finite set, and this is capital I is countable. So this is countable union of finite sets. It means capital K is countable, right? You know that countable union of countable sets is countable. So basically these VIs are finite and hence countable. So K becomes countable. So third condition, that is that local finiteness condition, forces K to be countable. So K, and here we can write as an open and this open cover of Rn has a countable subcover. So as I said, we will be mostly concerned with finite simplicial complexes, that is those which are having finitely many simplices. We will be concerned with finite simplicial complexes, that is those K having finitely many simplices. This makes the third condition redundant. Now we will define orientation of a simplex. Definition. An oriented Q simplex of K of some simplicial complex K is a Q simplex S belonging to K together with an equivalent class of total orderings of the vertices pieces of S. And so what will be the relation for so this equivalence class will be with respect to the relation given by this two orderings being equivalent equivalent if they differ by an even permutation. Even permutation of the vertices. Okay. Uh, for example, if we consider this, uh, uh, right, this ordering and this ordering, these two ordering they differ by they don't differ by an even permutation. They differ by odd permutation, right? This 0, comma 1. So 0 goes to 1, 1 goes to 0, right? So these two will give different, these two orderings will give different equivalence classes, right? They will belong to different equivalence classes. For example, if you take three vertices, V1, V2, V3, right? And then if 3 and then V naught and then V1, right? This and then this one. So if you consider this permutation 0, 1, 2, right? So this is an even permutation, right? So if you apply this on this, then this 0 goes to 1, right? So here, so this, so this and this, they differ by this permutation. This is an even permutation, right? So they will give a same equivalence class, right? So in place of that, if I just consider this P naught, V3, sorry, this was 3, 2, 2, right? So this V naught, V2, V1, right? So this and this, they differ by an odd permutation, right? So they will not belong, they will not be in the same equivalence class. So one can easily see that there will be only two equivalence classes in this with respect to this relation. If V naught, V1, and so on, VQ are the vertices of S, or the pieces of S, then V naught, V1, VQ denotes the oriented Q simplex, Q simplex of K consisting of the simplex consisting of the simplex S together with the equivalent class of the ordering this of its vertices. So this will be the notation to represent basically oriented Q simplex, right? Uh, with this ordering of its vertices. Now, first, for every vertex, V of K, there is a unique oriented zero simplex, this for every Q simplex with Q greater than equal to 1, there correspond exactly two oriented uh, Q simplices. Next, we discuss uh, we have listen, the standard n simplex delta n is defined as n equal to T naught, T1, Tn in Rn plus 1 such that the summation Ti I equal to 0 to n is 1, and of course Ti is greater than equal to 0. So one can see clearly that here these vertices are the uh, uh, these vectors EIs, standard basis vectors EIs. So clearly vertices of 10 are the union of all the faces of delta n is the boundary of denoted by the open simplex the open simplex this is this that is the interior of pair of this. Next, I will define a delta complex. So definition: a delta complex. A delta complex is a generalization of this simplicial complex. You can say structure on a space X is a collection of maps sigma alpha from the n standard n simplex to x with n depending on delta, such that first the restriction sigma alpha over the interior is injective and each point of x is in the image of exactly one such restriction. This image of exactly one such restriction sigma alpha, or this second condition is each restriction of sigma alpha to a face of n is one of the maps sigma beta delta n minus 1 to x. Here we are identifying the face of n with this by the linear homeomorphism between them. That preserves the ordering of the vertices. Then there is third condition, that a set A in X is open if and only if sigma alpha inverse A is open in delta n for each mark. Uh, so first remark is thinking of a delta complex X as a quotient space of a collection of disjoint simplices it is clear that X must be housed up. So we can see this delta complex X as a quotient space of disjoint simplices, and from that we conclude that the X must be uh, if there is a delta complex structure on X, then X must be housed up. From condition 3, this is a homeomorphism onto its image. So sigma alpha, this can be thought as an open as open n simplices. Because this delta n interior, this is homeomorphic to this it is homeomorphic to n cells. N cells means here I can say that this ball, you can say this n ball in, right? So unit n ball, you can say this, or you can say this dn. This is the closed unit disk, right? Its interior, right? So this and this, they are homeomorphic, and this is homeomorphic to this. So we can say that this is, so n cells are basically what? These are, they are interiors of this Closian bar, Closian disk, right? So next we have this gives a CW structure on X with this as n cells, alpha and sigma alphas and sigma alphas as characteristic maps. So basically, we will see some examples. Basically, what we have here is uh, we have simplicial complexes, simplicial complexes, then delta complexes, then CW complexes. So every simplicial complex is also a delta complex. Every delta complex is also a CW complex. So this is generalization of this, and this is generalization of this, right? So we will discuss some examples of this.